Now, next is inverse Laplace transform, again basic. We'll not go deep into this, we just do basic. As I said, this is first year undergraduate mathematics unit for physics students. Okay, so we want to find the inverse Laplace transform of the following function. So we'll not derive anything, but just recall the following. Recall that Laplace transform of 1 is just 1 over s. You also recall the Laplace transform of E at is 1 over s minus a. So inverse means we are now moving from here back to this. So it's just the same table, but now we are going opposite. Laplace transform of t power n, you recall that is n factorial over s power n plus 1. Laplace transform of sine at, you can recall this was a over s squared plus s squared. And lastly, Laplace transform of cos at was s over s squared plus s squared. I was forgetting the first shifting theorem. So for the first shifting theorem, the Laplace transform of E bt multiplied by our function of time is simply f of s minus b. We shift it by b. So this is very important thing to recall. Okay, so now find the inverse Laplace transform of f of s and all that. So we have two functions here. We are going to get the inverse Laplace transform of 4 over s minus the inverse Laplace transform of 2 over s minus 3. So you can clearly see this one is 4 over s. So 4 times the inverse Laplace transform of 1 over s minus 2 times the inverse Laplace transform of 1 over s minus 3. So if you look at this, you can see our a is 3 and this is 1, because the Laplace transform of 1 is 1 over s, while the Laplace transform of 1 over s minus a is 3, and the whole of this is e power 3t, because the Laplace transform of a e a t is 1 over s minus a, and our a is 3, so we just replace a by 3. So it means our ft function is equals to 4 times the inverse Laplace transform of this, which is 1, minus 2 times the inverse Laplace transform, which is e power 3t. And the answer will be 4 minus 2 e 3t. So we move to the next one. So still applying the knowledge here, we're just doing the reverse. Now on this one, we have the inverse Laplace transform of course 3 into 1 over s minus 2 plus 12 times the inverse Laplace transform of 1 over s power 4. So, here, of course, you can easily see this is an exponential. An exponential is taking that form, 1 over s minus a, but our a is 2. So the first thing, identify a as 2. So this is just e power 2t. Now here is 1 over s power 4, identify n. N must be 3, because if you follow n factorial over s n plus 1. So if you look keenly here, you find 12 here. So let me move this and say n factorial. So we have n as 3. So we have 3 factorial on top, which is just 3 times 2 times 1, which is 6. So the entire thing is, we have 2. So we'll have 2 times the inverse Laplace transform of 6 over s power 4. So you see this 6 times 2 still give us 12, but 6 is the same as, so we can move and say 2 times the inverse Laplace transform of 3 factorial over s power 4. Now we can now get our answer and say this is just 2 dot t power 3. Yes, because t power n is n factorial over s n plus 1. So our n is 3 plus 1 give you 4, and now 3 factorial gives you 6. So the whole of this simply give us 2t cubed, because that. So the whole of this one, 6 here, is the same as 3 factorial over s power 4. Now this takes the form of this. Now, our f of t will simply be e plus 2t cubed. Now we proceed to this part. Now the first thing we check on the denominator, we complete the square, because we need to solve for this problem. Because if you look at our Laplace, we have a square at the denominator. So the only thing you need to do is to manipulate this function to look like one of these ones here. Then you know you can go reverse, whether it is cos AT, sin AT, EBT, FT, t power n, EAT, or 1. So the first thing we are going to do, we are going to complete the square at the bottom. So at the denominator, we have s squared plus 4s plus 13. So completing the square here, we need to look for a way we can solve this to have a square here and a square the other side. Sum is 4 and 13. So what do we have as that? Okay, let me check. So we can write this as s squared plus 4s plus 4 plus 9. Yeah, because 4 plus 9 is 13. But remember, we can do here So we can factorize this part because we just need to look away, we can factorize the denominator. So s squared plus 4s plus 13, but 13 can be in the 4, can be splitted as 4 plus 9 because we can't factorize it. If you try two numbers, when you multiply, will give you 4, and when you add, will give you, when you multiply, will give you 13, and when you add, you get 4. You can't get that. So that is why you look for the way you can split this. So when you do that, this is actually what we get. On this part, the two numbers are likely to be, their sum is 4, and this is just a perfect square, and their product is 4. So the numbers is the roots is just 2 and 2. So that is exactly what we need. So 2 and 2. So we are going to have s squared plus 4s. 4s is now going to be 2s plus 2s. So s squared plus 2s plus 2s plus 2s, which give us 4s plus 4, now plus 9. So when you work out this, you complete this, you can see this is s squared, and our constant here, we can, okay, in fact, you know what we do. We don't need, if you don't want to go through all this, because we are not doing completing, we are not doing the quadratic function, then we can rewrite this as s squared plus 4s plus 2 squared, then plus 9. Now you complete the square by only picking the squares. So s plus 2, then you square, then also 9 can be 3 squared, because we just need our denominator to look like s squared plus s squared. So let's see what we have in the numerator. The numerator, we have s plus 5. So we need the numerator to look like this shift here. You can see the shift here is 3 plus, is s plus 2. So the shift is 2. So we need to make this one look like this. I think that is the next thing we need to think of. Now, we'll have s plus 2 plus 3. We are just looking for how we can make s plus 5 to have s plus 2 inside. Good. Now, our entire thing, which is now numerator, let me write here n. Now, numerator over denominator become s plus 2, then plus 3. Divide this one by s plus 2 squared plus 3 squared. Good. So that is how we are proceeding. Now we can split the function, and this is how it's going to be. We can split it as s plus 2 over s plus 2 squared plus 3 squared, then plus 3 over s plus 2 squared plus 3 squared. You have splitted this function. So we have s over the denominator, then 3 over this. So look at these functions. Let's try to figure out what happened. So let's assume this is our s squared, and this is our s squared. And you can see this look like that. So this is s, I'm assuming. On this case, again, assume this is s squared, this is s squared, and this is our a, because you see 3, 3. And then this is s. Now let's recall our functions. We know that for cos at, we have s over s plus s squared plus a squared. That is for cos at. Again, for sin at, we have a over a squared plus a squared. So automatically you see on this part, we can see something similar to sine. And on this part, we see something similar to cos. We can confirm that from top here. So sine we have s, and cos we have s. So we can see s, and then we have s. But something is shifting. That is what you should know. You can see we don't have just s, but we have s plus 2. So we also need to recall that if you have f of t, okay, let me put it well. You also need to recall if you have e bt f of t. Now we can have e bt, our f of t we can take of cos at. Then it will shift this way. It will be cos at, so we need s on top, so s is shifting by b, so s minus b over s minus b, because we shift it by this factor we multiply, squared, then plus a squared. Now let's express the one for sine. So e bt, then f of t. Now if we have e bt and then sine at, and then sine at, then we have our a over our s is shifting, s minus b squared plus a squared. So look at this and look at this. So we have a plus, means that our shift is negative. That's all. So now let's have our answer. So our answer will be, let me put it here. For the first case, we'll have cos, because we see s there. And it is shifting top and down. And you see negative is for positive b. So the first thing we identify, our b is equals to negative 2. That's what gives us positive. If it is 2, then it gives us negative. So our first function, we have f of t will be equals to e negative 2t times cos at. Our a from this particular diagram, or you can see our a is 3. So plus cos 3t. Then plus e negative 2t, again b is negative, then sine 3t. So we can factorize this by saying e into negative 3t into cos 2t, then into cos 3t plus sine 3t. Then we close. Now that is what we have by applying these conditions here. You just need to manipulate and make sure that you have the right thing. Now the last one, we are going to use partial fractions, because we have to express this as a partial fraction. So we have s plus 3 over s minus 1 times s plus 2 in form of partial fraction will be a over s minus 1 plus b over s plus 2. Because we have this denominator and this, so we can express this as a partial fraction. Now we multiply through by the LCM. So when you multiply through by the LCM, then here we cancel these two. So, okay, I can indicate times our LCM, which is the product of the two, again times our LCM, product of the two, times our LCM, product of the two. So here we define our LCM as S minus 1 times S plus 2. Good. So when you do that, this is what you get. This cancels the LCM, so it is S plus 3. On the other hand, the negative cancels the positive 1, the negative 1, so we go to the positive 1. So S plus 2, because this will cancel S minus 1. Then plus B into, now the positive S plus 2 cancel itself, so we get S minus 1. So we expand, we have S plus 3. We can use simpler method. So we can solve for B first. We can solve for A. If you want to solve for A, then you make B 0. So we want to solve for A, we make the B part to be 0. So to make this B part to be 0, then we say S is equals to 1. So for B part to be 0, S must be equals to 1. So we are going to have, I don't know why I'm unable to wrap this. So S is 1, so we are going to have, solve for A, so we are going to have S, which is 1. So we are going to have 1. Okay, let me use a black. So 1 plus 3 equals to A plus S is 1, so A times S is 1. So this part will be 1 plus 2, 3, so we'll have 3A. So A plus 2A, then plus 0. So we'll have 4 to be equals to 3A. And A will be equals to 4 over 3. Now to solve for B in the same equation, you make A 0. Now making A 0 means S is equals to negative 2. And by doing that, A will be equals to 0. So can we proceed? We are going to have negative 2 for S plus 3 equals to A. So we have here as negative 2. So that is 0. So A will be 0. Then plus B. S is negative 2. That is negative 3. So negative 3B. Now this one is negative 1. Now that is positive 1 is equals to negative 3B. So it means B is equal to negative 1 over 3. I don't know what has happened. I've lost everything. This is so strange. Software problem. I've already written some few things here. Why am I not able to see them? Let me see if I can write again. I can repeat. Let me see if I can now. Okay, let me repeat it again. Partial fraction. So partial fraction will have f of s. We are going to express as a partial fraction. So we'll have s plus 3 all divided by s minus 1 into s plus 2 will be equals to a over s minus 1, then plus b over s plus 2. So we are going to multiply each by the LCM. So times the LCM, times the LCM, and times the LCM. Now here, our LCM is the product of the denominator. So LCM equal to s minus 1 times s plus 2. So what happened? The other part cancelled the LCM, so it is just s plus 3 equals to negative, cancel the negative, so it becomes a into s plus 2, then plus b. The positive cancel this, so it becomes b into s minus 1. Now we want to solve. So if you want to solve for a, then s must be equals to 1 for b to be equals to 0 here. So what happened? We are going to have s. Of course, our s is now known. S is 1. So we are going to have 1 plus 3 equals to a into 1 plus 2, which is 3, then plus 0, because we have to solve for a. So s is 1, that means this part is 0, b will be 0. When you do that, you'll get 3a equals to 4. I already did this, I don't know what happened. Everything clears up. So we are going to have our a equal to 4 over 3. Now, to solve for b, s will be equal to negative 2, because when you put negative 2 here, a vanish. So it means a will be equals to 0. So now we have negative 2 for s plus 3 equals to 0, because negative 2 plus 2 is 0, so a vanish, then plus b into negative 2 minus 1. So this is negative, this is positive 1, while the other side is negative 3b. So it means b is negative 1 over 3. Now our fraction become our a, which is 1. Our a is 4 over 3 over s minus 1, then plus, remember this is a positive, so plus negative a third over s plus 2, which is the same as 4 over 3 into 1 over s minus 1, then minus a third into 1 over s plus 2. So this looks like the exponential. So the Laplace, so what we are going to have is, now that we have seen exponential here, we are going to do the inverse Laplace transform. So 4 over 3 times the inverse Laplace transform of 1 over s minus 1 minus a third times the inverse Laplace transform of 1 over s minus 2. So that you see we are still having the same, but a is negative 2. So here a is equals to negative 2. This is just the same as s plus 2. And here a is equals to 1. So our exponential, you recall that e power a t, the Laplace transform is 1 over s minus a. So in the first case, our ft, which is our function, will be 4 over 3 dot et. Why? Because a is 1. So s minus a is et. So a is 1, so it remains et. We are doing the reverse. So we are moving from here back to here. Minus a third dot e negative 2t. because a is negative 2. So we go back from s minus 2a, it go back here. So a is negative 2. I hope that is it. Yeah. We can simplify if you want, but I think that's all. Okay, so this marks the end of Laplace transform, the basic. We didn't go deep. Maybe deriving the table might be difficult, but it's just basic integrals. We just did some basic integrations on exponentials and then apply. We avoided the partial integration to solve for the sine AT and cos AT by going through the Euler formula, which is the easiest way to derive the Laplace transform of cos AT and sine AT. So once you master the table, you just manipulate your functions to look as what is to look like one of the functions in the table that you know their standard Laplace, and then you factorize or you substitute, and you get your result. Otherwise, this marks the end of basic Laplace transform and inverse Laplace transform.